I'd like to invite Dr. Patrick Walker, who's a lecturer in infectious diseases with the MRC Center for Global Infectious Disease Analysis at Imperial College in London, to give us some insights from modeling into what we might expect from treating school-age children.
Thank you. Thank you. So thank you very much, Julie and Miriam, for inviting me to the symposium. It's really exciting to be here. So this is just some modeling work, which, like most good modeling, tells us what's already been covered today. Miriam did a really good summary of basically everything I'm going to say. But at Imperial College, where I'm based, we have a reasonably large group of modelers, and with a model going back about 10 years, which I had no role in developing, so it's kind of not got that downside to it. What it does, effectively, in simple terms, it models the relationship between mosquitoes and people, how malaria transmits between them, and then kind of onwards through the transmission cycle. And this is then modulated by the, whatever you want to call it, the receptivity, the vectoral carry capacity within a setting, which has things related to rainfall, temperature, perhaps land use or whatever. And so you can kind of calibrate it to whatever level of transmission you want, and how that varies through time. So within the model, it's quite complicated, but I won't get into too much, but there are various forms of immunity, which is some of the things that we're sort of getting into. Some of that occurs before the infection reaches the bloodstream. Some of that works within the bloodstream in terms of controlling densities and actual onwards infectivity to the mosquito, in terms of things like gametocyte densities. But kind of more dramatically, and the more sort of apparent and marked, is the immunity to disease, which is what we're sort of mainly concerned about in general. So it also acts to reduce clinical disease, and also the severity of that clinical disease when it occurs. So so this is a whole range of model fitting that I wasn't involved in, and I'm going to call out Jamie Griffin, who was formerly of Imperial, but now is at Queen Mary's at University of London. And they've done loads and loads of fitting to a lot of data to capture these relationships between transmission, between the risk of being infected, and then what happens when you are infected in terms of your clinical disease and the severity of that illness when it occurs. But I'll try and kind of summarize that a little bit more in terms of actually just a kind of simple pictogram. So what happens? So if I was to find myself in the model, given I've never had malaria and I'm to most intents a grown-up, it wouldn't matter that my age. The first time I was infected, I would get really sick. It might cause something very severe that I'd need to go to hospital for. I might not recover from it. Then, if I do, then I get infected again and again, I'm likely to get sick, but over time, my symptoms and severity will come down. Eventually, I might get to the stage after a lot of bites and a lot of infections where I'm not getting many symptoms, maybe just, like was covered by Miriam, maybe a bit of anemia or something like that. And then, but I'm also not likely to get treated, but I also might have a reasonably, a substantive blood stage infection reaching high densities. It's quite infectious. Eventually, I'll have no symptoms, and as I'm getting more blood stage immunity, it'll regulate the density and clear it quicker, to the extent that, by the time I've had lots and lots and lots, I might not ever get a detectable infection, or if I do, it'll be very short-acting. So that's what would happen just without age in the model. There are age components around things like immune competence and other things, but in general, that's the thing, and that then determines generally the patterns of disease that you will see with age, and I will discuss how that relates to school age. So in areas of very high transmission, you're very likely to have infection early on, more likely to. So that means that people who, the very sick are at younger ages, and sick, still at quite younger ages. And then the older individuals are, generally speaking, within the model fine when they get infected after enough bites. If we then decrease transmission in the model, you get something a bit more like this, where there are fewer bites as you're growing up. And that means that in terms of, you will probably get sick fewer times over your lifetime. You'll hopefully experience a lower burden. But actually, when you do, you're likely to be a little bit older. So the severe diseases might creep up into older children, and cases might even start to affect adults. So what does that mean if we actually just now move from this pictogram to what the model actually gives you in terms of output? So, like I said, there's some other age-driven effects, but in general, what you find is that as you increase transmission, so here I'm measuring transmission slide prevalence in 2 to 10-year-olds, it stays fairly flat to begin with, but as you increase it, you get this kind of peak in older ages. And if you look at the more severe diseases, that peak is far more accentuated, because that's where in these higher transmission stages, you are acquiring that immunity a lot more quickly. So if I didn't know this was an infectious disease, I would probably, looking at this, spend my first resources here, and in the younger kids in the high transmission setting, and then I might expand out to the older kids, and if I have a bit more money. But if I look at how that sort of here I'm just showing the proportion within each age category as a function of this continuum of transmission slide prevalence in 2 to 10-year-olds, and this is just showing where you have the purple being the proportion of cases in children, the red being the proportion of cases in adults, and then you've got sort of 2 categories of school-age children in between. You can see that you get this move from high burden concentrated in younger kids as a very high transmission, and then it gets more spread out to sort of reflect the demographics, the proportion of the population within each age group. And school children just sort of stay in the middle. Severe disease, it's more pronounced, again, for the same effect. And here, because it's quite hard to follow what's going on in this part, and that's what we're talking about, here I've just plotted that proportion here. And what you would suggest is actually the clinical burden is fairly consistently, it's a reasonable chunk of the overall number of people who are getting any type of illness in the population. It's more than the proportion of the population school children represent. But because these more severe disease are the earliest infections you get, you do get this sort of peak where the highest sort of when they're contributing the most to the severe disease within the population. That's in the lower transmission places. Thanks, Judy. Okay, so that's what the mosquitoes are doing to the people, but also you've got to think, and this is what a model is quite good for, to think about what the people are doing to the mosquitoes in terms of the full transmission cycle. So what are they transmitting to mosquitoes? Well, what do you need to transmit an infection to a mosquito? Well, you need to be infected. So if we take this as, again, just repeating the pattern of clinical burden with levels of transmission, and here I'm just going to plot what the slide prevalence would be predicted by the model at these 3 different transmission intensities for a completely perennial setting, and see what that looks like. And I'm using slide microscopy because that's a fairly dense infection that probably can transmit relatively well. And that's where you get a completely different picture. So that's where you find that actually it always tends to peak in around older children, maybe some even beyond school age, eventually very low. But you get this big peak here in the highest transmission setting. And there's a few reasons for that Miriam covered very well. I've got one to add. So that's the fact that school children are bigger than younger children, so there's more of them to bite. They are less likely to have symptoms as you increase transmission, and if you have symptoms and you get treated, you're no longer infectious. If you don't get treated, you'll stay infectious for a long time. Stay infected for a long time, I'll go on to infectious. But in these areas of very high transmission, by the time you reach adulthood, that's where we're getting to these people who are really getting fairly good immune responses. So they have fairly low densities. So if this was PCR prevalence, there would be an older peak again, but I'm just using it because it kind of maps onto infectivity to a degree. So what if we now factor in these changes in biting patterns and the changes of infectivity as a function of density, or in the case of our model, we link that with detectability. Do that. This is that. So I'm just going to remind you, this is what the proportion of the clinical burden is as a function of age. If we now do that in terms of what the proportion of onwards infection, what proportion of infected mosquitoes are within each category, you see that now, because prevalence is fairly stable, slide prevalence is fairly stable, and biting is preferentially in children, in the older age people, you see, let's go back, there's actually a fairly stable proportion of the population in school age that are the ones who are affecting mosquitoes. So it's about, we'd estimate about 45% to 40 to 50% of mosquitoes generally of infected mosquitoes have got their infection from a school-age child. And so adults might be a bit higher in some places, but that's because there are more adults than school-age children. So actually, really, the school-age children, at least in the model, are the engine that the parasite relies upon to kind of push the transmission throughout the population. So that's good for the model, but it's always good to do a sanity check. So this is from a really cool paper by Bronner Goncalves and Chris Drake, who was in Chris Drake's group in the London school. And they actually managed to find a lot of mosquitoes, find blood in mosquitoes, and link them, genotype them to people in the households that they caught them, to look at the proportion of infections that were caused by different age groups. They also looked at biting rates, and they also looked at infectivity with blood feeding assays, and they also looked at the prevalence to get some sort of estimate, kind of mapping onto what that I've just shown you in the model. And that's just kind of, I'm highlighting what it shows there. And it kind of looks like our estimates of, say, 40 to 50%, at least being an engine room of pushing infection, are, if anything, perhaps even slightly under, but they're not too bad. They definitely seem relatively sane. So now we've got the full transmission cycle. We can start to look at what happens if you do target these school-age children. So this is SMC is one thing that targets children, and this is work I've been doing with Matt Cairns from the London School. And here what we do is we calibrate the model at a fairly fine spatial level to the sort of the average level of transmission as measured by the Malaria Atlas Project, and the extent to which transmission is distributed through the year, extent to which it has a seasonal peak driven primarily by rainfall. So if we model that, we can then alter the age at which we're delivering SMC to the model and see what impact that has. So this is the impact this is direct impact. So what's happening within the age group receiving the SMC? So in 0 to 5, this is at 80% coverage at 6 months to 5 years, current general practice. You see this really nice big impact, especially in seasonal places that have high transmission. So this is the impact it's having in terms of the severe cases averted. As you then move that age group, so looking at up to 10 as they were doing in Mali, you then would see, it still has a substantial impact on burden, but here it's not so much linked to transmission, it's more, transmission intensity. It's actually, this impact is driven more by seasonality. In other words, because some older children are more immune in the higher transmission setting. So it's really just what proportion of the burden window are you catching with your SMC. And as you move into the older categories, the impact is becoming less, as you'd expect, because these children are now getting immune profiles in the higher transmission places with the highest burden that aren't too far away from what an adult would have. Okay, so that's the direct impact, but the good thing with the model is you can then look at the people who didn't receive the intervention and say, well, what was the indirect effect? What did it have a reduction? Now, for under 5s, because under 5s are a very small proportion of the transmission reservoir, we're probably overestimating them, if anything. We're estimating fairly negligible impact on transmission due to SMC. But as we push SMC into the older age groups, we start kind of stalling the engine of the parasite because we're starting to attack where it's like prime real estate is. So here you can see that you're getting kind of reasonable impact. So here the sort of these greeny things are sort of roughly a 25% reduction. As you push it even further, you're tackling more of the parasite reservoir, therefore you're having a bigger impact on transmission. In some of these places it's fairly substantial. Now again, it's good to do a sanity check because we haven't actually done any fitting on this indirect effect of this age group in particular, but then there's not a whole lot of data to inform it, but kind of eerily, and I promise we didn't cheat, this is the only one that I know of in the literature, and if anyone's got any more, I'd really like to so it looks a little bit less like we cheated. But it was like a 25% reduction in this place in central Senegal, and that's basically what the model spat out. So that at least looks like we're we're not producing anything that's insane here. Okay, so all of this that I've been showing so far is just assuming that all other interventions are the same and we just target the school kids. But actually, as my colleagues from Uganda were just discussing, all interventions aren't the same with age. And actually, it's not just a Uganda problem. So it's going to be really interesting to know how they did it in Mali, because you can look at almost any survey and you'll find, this is from a very recent, very useful paper from Noor et al. In Malaria Journal this year. You find that there's a typical pattern with age. What you get is very young children have the highest use, that then declines as you reach school age, and as you get older school age, it reaches a sort of a nadir, it reaches a trough, and then you get this big jump as you reach adulthood, and it kind of tops off again. And it seems to be the more intense, this is 10% transmission, 10 to 20% transmission, 20% and above. The higher transmission, the more you're trying, the bigger a gap you get. Well, that's another thing we could look at in the model and actually say, what impact is this gap having? So if I take the Noor et al. Relationship with age, this is from, if I go back, this was from, I think, 5 or 6 countries, I can't remember exactly. I think most of them were in East Africa, but I'll show you an example in West Africa in a minute. And we could say, well, what if it's a very high transmission place? If it's a very high transmission place, then you would expect, so this is just a sort of 60% prevalence in 2 to 10-year-olds, you would, it's not good that there's this gap, but actually at least we're covering those most at risk. So in some ways, although it's not perfect, it's kind of, it's a little bit tailored. So we can simulate that impact. So here, this is when there's no intervention. Here, it's just this is what the also average clinical in the population. And if we simulate it, you get a nice impact here, because it's not huge, because we're still taking the overall average of about, what is it, like 30% use. And then we could also play around in the model and look at what happens if you just have the same average use, but just completely flat. And see, what our sort of tailored strategy is looking like. And weirdly in this model, not weirdly, I'll rephrase that, it's actually showing very little difference. And that's because actually LLINs are, to a big degree, targeting transmission. They're transmission reducing interventions. And currently, they're missing out the people who are contributing the most to transmission. So we can start playing around by looking at what happens if we close this gap. And it's quite fiddly to get these things right, so I slightly missed it in the old categories, but it'll do, hopefully. And see what closing that gap looks like. And it has some impact. I mean, we're only talking a change in overall coverage of, say, 3 or 4%, so we probably always want to be, kind of tempering our expectations somewhat. But we can sort of say, well, what are we losing because of this gap? And in this simulation, we were losing about 11% due to this gap that we have in the school-age kids. Now, this is an overall average across multiple countries, and actually, unless there are some places where school children have more bed nets than anyone else, which seems unlikely in general, we could actually speculate that some of this, so there will be probably quite a lot of heterogeneity in terms of underlying coverage within this. So we could actually think about what happens in a place where there is very good distribution of nets. But there is still this gap. So this is just a hypothetical one, but I'd be tempted to bet that you could find an age pattern in various places that looks somewhat like this. So you could simulate that impact, which is giving a bigger impact because it's a higher overall usage. But then closing this gap with the green dashed line here, so we would just put in a usage profile with age that closes this gap. You're then getting a fairly sizable chunk of the burden that is attributable to this gap. So here, because we have this gap is causing, in this simulation, about a 33% increase. So we're still kind of early days getting into these age-dependent profiles, but it's going to be a sizable chunk. It's maybe not going to make the difference between elimination and not elimination, but a 33% reduction or even a 10% reduction these days would be quite a big achievement given current trajectory of malaria globally. Last thing isn't really to do with modelling. It's actually to think where we're talking about use and age and school-age children, and actually when you look a little bit deeper at these surveys, it's not necessarily all to do with age. It's a bit more to do with life course. So here I've taken for Ghana, so this was to show that there are these similar things in West Africa. It's a little bit of an old survey, but I think you could find loads of examples where it's the same, where you look at female patterns of use, male patterns of use, where you're getting this gap and then it comes back. But actually, if you stratify by whether or not a woman is going to have a family, whether she's pregnant or she's ever had a baby before, the age effect pretty much disappears, or at least it stays declining all the way through up to adulthood. And actually, it's in the women who have been pregnant or have a child where use is actually generally pretty high. So it's the point that this isn't just age, it's life course. And if we think about what would happen if we managed to cover this gap and promote PAPC prevention, well, when we think about people becoming adults, starting to have a family, we have malaria and pregnancy. And when is it most important to be using a bed net? Well, before your first pregnancy, because that's where you are most vulnerable to, because you don't have any pregnancy-specific immunity. And that's the time in your life when you're least likely to be using a bed net almost uniformly in any place. So actually, I'd argue that in terms of closing this gap and sort of promoting any prevention tools that we can find, you can see a big impact, not just on the direct health of the children themselves, also the rest of the population, because they drive a lot of transmission, and even feasibly kind of across generations, because as you're part of your life course, you take a lot of things from school into adulthood. So, so not a lot of answers in terms of what the best thing to do is, but I think it's fair to say when we're talking about targeting school age, often what we're talking about is trying to avoid leaving them behind, because currently they are being left behind. And they're a constant, fairly major contributor of clinical burden, and often the main and probably the highest per person contributor to transmission. So just promoting prevention practices in these age groups could easily, I think, have fairly important kind of cross-generational impact on maternal neonatal health. So I think, it's my acknowledgements. So just to acknowledge, there's various people in my group who I've missed. But Jamie Griffin now at Queen Mary, Pete Winskill, who helps with running the model, the organisers, Matt Cairns for the London School, and funding for Medicines for Malaria Venture. And to you all, thank you.